Hello everyone, my name is Zixuan. I'm a PhD student at iPad Lab Shanghai Jiao University. Today I'm really excited to present our research paper, ODRP, on-demand remote paging with programmable RDMA. So in modern data centers, the memory demand of memory-intensive applications such as k-means, graph processing databases, and memcached varies over time. To ensure the performance requirement of these applications, data centers often over-provision memory to meet their peak usage, which leads to low average memory utilization. As a solution, disaggregated memory architecture is gaining popularity in modern data centers. This architecture separates CPU and memory resources into two network-attached hardware pools, namely compute nodes and memory nodes. Compute nodes have abundant CPU cores but limited local memory, while memory nodes have large memory capacity but very limited computing power. Our work focuses on disaggregated memory architecture based on RDMA network. RDMA provides highly efficient one-sided memory access primitives, allowing compute nodes to access remote memory with ultra-low latency. Besides remote memory access, in disaggregated memory systems, memory nodes also have to manage memory by handling allocation and deallocation requests from compute nodes and ensure memory isolation between different compute nodes. For this purpose, RDMA provides a control path operation called memory region registration. A memory node can allocate a memory chunk to the compute node by registering the memory chunk to the RNIC as the memory region and sending its metadata back to the compute node, including the memory region's address and R key, which is the access token. Then the compute node can access the allocated memory with this address and R key. Based on memory registration, a disaggregated memory system can perform fine-grained memory management intuitively. To be specific, memory nodes register small memory chunks, small memory regions, and allocate them to different compute nodes dynamically, achieving high memory utilization due to its fine-grained allocation. However, this approach can significantly degrade the performance of compute node because it requires the compute node to frequently send memory allocation and deallocation requests. And the time-consuming and CPU-intensive memory region registration process can also become a performance bottleneck in the whole system, especially with the limited computing power of the memory node CPU. Therefore, most existing disaggregated memory systems adopt a static memory management approach. For example, FastSwap, a state-of-the-art swap-based disaggregated memory system, registers memory regions with the size of swap space of the compute node. This approach achieves high performance since there are few or even no memory allocation requests during runtime. However, it inevitably leads to poor remote memory utilization due to severe internal fragmentation. So existing disaggregated memory management approaches cannot achieve high performance, high memory utilization, and no memory node CPU usage at the same time. To address the above limitations of the existing approaches, we propose ODRP with three design goals: fine-grained memory management for high memory utilization, fast data path allocation for high performance, and no memory node CPU usage to achieve full disaggregation. To meet these three design goals, ODRP leverages a less explored hardware feature called RNIC offloading. RNIC offloading supported by commodity RNICs. It's enabled by two key hardware features. The first one is called event-based worker request triggering. Specifically, commodity RNICs support a special verb called wait. Wait can suspend the execution of a work queue, wait for another work request to complete, and trigger subsequent work requests when receiving a request from the compute node. The second feature is that we can chain basic work requests like RDMA read and RDMA write together to express complex logic, because previous work requests can actually modify the arguments of subsequent work requests. Here is a simple example of implementing a function using a work request chain. The function takes two inputs, x and y, and compare their values. It returns 1 if x equals y, otherwise it returns 0. In the work request chain, the first received work request places x in the out field of the subsequent compare and swap work request, and y in the opcode field of the third work request. If x equals y, the compare and swap will modify the opcode of the third work request from no up to right, updating the final result from 0 to 1. Otherwise, the third work request remains no up, and the final result remains 0. This example demonstrates how chaining basic work requests together allows the RNIC to enable one-sided operations with richer semantics. ODRP leverages this RNIC offloading feature to offload memory management and memory access logic to the memory node's RNIC, enabling compute nodes to efficiently allocate memory in data paths on demand. This figure shows the high-level architecture overview of ODRP. ODRP is a SOAP-based system. On the compute node side, ODRP provides a SOAP backend that can direct SOAP requests from the Linux kernel to the memory node. At the memory node side, it divides its memory into fine-grained 4 KB pages and maintains two types of metadata. First, it uses a ring buffer-based free page queue to manage all the free pages. Second, it maintains a transition table for each compute node that maps the compute node side SOAP addresses to the memory node side page addresses. When receiving a SOAP request from the compute node, the memory node's RNIC executes the offloaded logic, which is the work request chains in this figure. The offloaded work request chains use these two types of metadata to perform memory allocation and memory access. Next, I will briefly introduce the workflow of a SOAP request in ODRP. When receiving a SOAP request from the Linux kernel, the compute node's SOAP backend redirects this request to the memory node using an RDMA send operation with necessary arguments. The request triggers the RNIC of the memory node to fetch and execute offloaded pre-programmed logic, which is the work request chain in the figure. The work request chain uses an RDMA read operation to read the transition table entry according to the SOAP address in this request, performing address translation. If the target SOAP address has no valid mapping in the transition table, which is a page fault, the work request will allocate a free page from the free page queue using an RDMA fetch and add operation on the queue head pointer and updates the transition table entry with the newly allocated page. Finally, it performs memory access with RDMA read or RDMA write, returning the result to the compute node. While RNIC offloading allows logic to be offloaded to the RNIC, it faces two critical challenges. The first one is efficiency challenge. In particular, more complex logic requires longer work request chains, which involves more PCIe round trips, and will lead to slower execution. So the question here is, how can we minimize the number of work requests per chain? For this purpose, we propose a software-based technique called compute node assisted principle, which can shift part of the computation to the compute node side to reduce execution latency of work request chains. First, we observe that the base address of a compute node's transition table can be securely shared with the compute node. So we shift the calculation of transition table entry address to the compute node and let the compute node directly provide transition table entry address instead of a SOAP address when sending the SOAP request. This can reduce the execution latency of work request chains. Second, we found that a compute node actually has full knowledge of the mapping status of its SOAP space because the transition table is initially empty and an allocated page can only be freed by the compute node itself. Based on this observation, we let compute node determine whether a SOAP address is mapped or not, avoiding complex and time-consuming page fault detection logic in the work request chains. The second challenge is functionality challenge. The memory node side free page queue is actually an array-based ring buffer, which requires mod operation. However, RDMA lacks native support for mod operation. In addition, the RNIC's antiness mismatches that of the host, meaning that the RNIC cannot directly use its computed value as an address to access host memory. In our case, this issue impacts the retrieval of allocated queue elements from the page queue. As shown in the figure, the fetch value of the queue head pointer by the fetch and add operation cannot be directly used for the subsequent RDMA read operation without antiness conversion. To overcome the above functionality limits, we propose two meta work requests. The first one is fetch and add with modular support. we make use of an advanced work request supported by a commodity RNICs called masked fetch add. By masking the upper base of the Q pointers, Q head pointers, and Q tail pointers during increment operations, we achieve the wraparound behavior. The second meta work request we propose is called endian swap. Instead of using 8 RDMA read operations to convert the endiness of an 8-byte value, we utilize an RDMA feature called scatter-gather IO and use one RDMA read operation with 8 scatter-gather entries to perform the endiness conversion, which can significantly reduce the execution latency. With this endian swap work request, we can efficiently convert the endiness of the fetch Q pointers and use them as the source field of subsequent read operations. So to demonstrate the effectiveness and efficiency of ODRP, we evaluate ODRP on 8 compute nodes with one shared memory node. Each compute node is configured with 12 GB source space, and the memory node uses only one CPU core to simulate its limited computing power. Each node is equipped with a 100 Gbps Connect X5 RNIC. We compare ODRP with 3 baselines: one-sided static, one-sided dynamic, and two-sided. One-sided static pre-registers memory regions with the size of the source space of compute nodes and uses one-sided RDMA operation to perform memory access. One-sided dynamic also uses one-sided RDMA to perform memory access, but it performs memory allocation in the granularity of 1 MB. Two-sided use two-sided RPCs in the data path to perform memory access. In our application benchmark, we run various real-world workloads such as k-means, memcached, and PageRank on 8 compute nodes. Compared to one-sided static, ODRP can achieve up to 12 times better memory utilization because ODRP can achieve ideal memory utilization through its page-level allocation, while one-sided static leads to severe internal fragmentation due to its coarse-grained allocation. ODRP achieves this improvement in memory efficiency with only an up to 14.2% performance overhead. In addition, ODRP does not require the memory node CPU involvement, effectively preventing it from becoming a performance bottleneck. In our scalability evaluation, we increase the number of compute nodes from 1 to 8, each running 4 quicksort tasks. ODRP only introduces an up to 14.6 performance overhead compared to one-sided static. Compared to one-sided dynamic, it shows 2.92 times better performance. To conclude, current disaggregated systems cannot achieve high memory utilization, zero memory node CPU usage, and high performance simultaneously. We propose ODRP, the first system leveraging RNIC offloading to achieve ideal memory utilization, zero memory node CPU usage, and high performance. Moreover, we introduced 2 software techniques to address the efficiency and functionality challenges of RNIC offloading. Our evaluation shows that ODRP can significantly improve memory utilization with less than 14.6 performance overhead in real-world workloads. Thank you for your attention. I'm ready to take any questions.